Hello, good afternoon and good evening, wherever part of the globe you are watching. This is your host, Mike Espina, and welcome to Math Agility Live. This is our platform where students can send in their math homework problems to our social media channels, and we will answer them via Facebook Live every Tuesday and Thursday, that is PST, and Wednesday and Friday, that is Manila time. And tonight, we have a special guest, and we will discuss about digital television and the mathematics behind this technology. Okay. And after his talk, we will have a short Q&A before we wrap up. So you can write down your questions in the comment section below and we will try to answer them. Okay. And before we start with this presentation, let me briefly introduce to you our speaker. So he is a professional electronics and communications engineer and a consultant. He is the co-author of the book Integrated Services Digital Broadcasting-Terrestrial, that's ISDB-T, a handbook for broadcast engineers. He has a master's degree in engineering major in control systems at the Mapua University, and he was a visiting research engineer at the NHK Science and Technical Research Laboratories in Japan. Please a warm welcome to Engineer James Rodney Santiago. Hi, James. Okay. While he's getting online. Okay. Hi, James. You can.
Hi. Okay.
All right. You can
Good
start.
morning or good evening to all of you.
Yes.
Okay, I'm gonna share my screen up. Maybe I should go slideshow. The good thing about work from home is that you get to sit back and relax, smoke, drink coffee,
Yes.
and do work.
Okay.
So I hope you're seeing my screen now. Yeah.
Yeah. Yes.
Okay. So this is one topic that is rarely discussed in the dissemination of the information about digital TV broadcasting. Even engineers try to minimize the discussion on the math behind it because i- in our experience during our time when we were studying this algorithms called transforms uh, are really difficult for most engineering student. But the advantage of the generation now is that there's a lot of computing power available that allows you to perform simulations and calculations almost in real time. We don't have that during our time. So it's about pen and paper and some assistance from a calculator. That's the limit of the technology during our time. Uh, but take note that these algorithms were even developed even in the time that we were not yet born. So there are a lot of great mathematicians who created proofs that they never thought that would become useful actually. So in their time, their main objective was just to get their PhDs because you have to create a thesis and you have to have this dissertation, international presentation. So their purpose was really totally different from what the industry uh, has taken into in using their algorithms. So I don't know if you've heard of Fourier Transform. He's a French mathematician. His equation or algorithm actually powered the technology, our technology now, and even in for the future. So um, we call it the Fourier transform. So many students hate this trend. Even I, when I was a student, I find it really difficult to understand because you have to solve it manually. But contrary to the difficulties in learning, The purpose of Fourier transform really is to actually simplify the expression or to get the result uh, from evaluating complex numbers, real and imaginary numbers. So I don't know, guys, if you're having an overload already. I was supposed to talk about digital TV broadcasting, but I delved into uh, I delved into um, the math behind it. So I'm laying down the foundation so that you will understand. Wait, yeah. So there are two major math equations or algorithms that we consider in digital TV broadcasting: the discrete cosine transform and the fast Fourier transform. So to divide the two, the discrete cosine transform is used mainly on the audio and the video, and the fast Fourier transform is being used in the transmission to manage multiple carriers. So the journey of broadcasting, actually, every new development is somewhat aligned to the the biggest sporting event in the world. That's what Olympics is called during our time, the biggest show on earth. So, what better way to launch and introduce new technologies by aligning those technologies in a major sporting event? So, if you would look in 1948, it was the first uh, TV broadcast, London Olympics. And then in 1964, it was the first uh, Olympics in full color. And then in 1984, it was the first recording in high definition. Can you imagine in 1984, there's already high definition? So I actually met and worked with the guy, the Japanese engineer who developed the high definition technology. He patented it in 1979. His name is Mr. Junji Komata. So we've been working together for about 7 years now, actually. So if you would see him, he looked like Albert Einstein because of the hair. He's really a smart person. So I never thought that I'd be working hand in hand with such an engineer with an illustrious career like him. So anyway, in 1988 was the first live broadcasting. So before that, all transmission uh, of broadcast from remote areas are taped. So it's only in 2008 that they've started live feeds via satellite. We don't use submarine cable at that time because it's all copper, and it would be hard. It would find it hard to cope up with the data rate requirement. In 2008, it was the first live uh, in full high definition. And then in 2012, Japan thought they could win the hosting of the Olympics, and they would launch the new technology. So if we're going to backtrack, in 1964, when they hosted the Olympics, it was a major turnaround for the broadcast industry because they introduced color television. So they wanted to launch the new technology. And it's not high definition because high definition was developed in Japan in the 70s. So they wanted to make the great leap, not even 4K. They're talking about 8K or super high definition. So, but they lost to London. So what they did is they lent the equipment to London for special public viewing of super high vision to some key areas. So they tried again in 2016 to relaunch, but they lost to Brazil. And then finally in 2020, they got the hosting rights, but because of the pandemic, so they they're kind of delayed again, or they're halted again. So uh, I feel bad for Japan. They've been trying to get this, and now that they got it, they are held back by the pandemic. So I have here the digital TV adoption map for all countries. So if you're in the US or in the North America, then you are using the ATSC, or Advanced Television Systems Committee. It was the technology developed by the FCC, and it's based on a single carrier system, much like what analog does. It's a single carrier system. So there was some debates in the early parts of the introduction of digital TV. This was in 1998. 1998 was the beginning of the publication of digital TV recommendations from North America and Europe. Now, Japan started opening up their own technology in 2003. So the major difference is that the North American digital TV standard called ATSC is based on a single carrier, and it's like analog. So it kind of carried the same problems in analog reception. It is susceptible to uh, echoes or ghosting or via reflection of signal. When I say reflection, there is a direct signal, and the reflected signal that bounced from a building, or if you try to move the receiving antenna, there will be phase errors. So those are pretty much obvious when you are driving and then you're trying to watch TV. So the reception would be difficult for a single carrier system. Now, for the Europeans, they developed a multi-carrier system called OFDM. It's a it's called orthogonal frequency division multiplexing. So instead of a single carrier, they use thousands of carriers. It can go up to 8,000 carriers. And then those 8,000 carriers would carry the information. Now, the difference now that you have multiple carriers, the same with Japan, they use the multiple carriers too, called BST or FDM, or band segmented transmission orthogonal frequency division multiplexing. Uh, the advantage of multiple carriers is that it can handle echoes, reflections, and then phase errors. So it allows mobile reception. For the Japanese standard, you can travel as fast as like 300 kilometers per hour, and then you will never lose reception because of the Doppler shift. It's well managed by the technology, including the error correction codes embedded on it. Now, how are you able to handle thousands of carriers and then transmit it? That's where the fast Fourier transform comes in. Now, the transformation simply would make an estimation of what a certain signal would represent. So by combining the fundamental frequencies and the second harmonics, third, fourth, fifth, until you reach 8,000 carriers, if you combine them, it can be represented by a single Fourier transform. So that's the beauty of it. So when it's transmitted, you apply fast Fourier transform, and then when it reaches your receiver, like a tuner box or your internal receiver in the TV, the chipset would perform inverse fast Fourier transform, and then you get to watch the program that you want. So the green ones in this picture represents countries that are using the European technology. And then the pink or red image are the countries using the Japanese standard. So in Asia, it's basically Japan, Philippines, Sri Lanka, and the Maldives. Uh, and then most of the countries in South America, and then there's one country in Africa. Okay, now in order to further advance our desire to reduce the amount of data to represent a particular image or audio, we need to understand the limits of the human eye and the human ear. So that way, we can apply simple concepts like redundancy and irrelevancy. So take, for example, in this image, we're trying to analyze our eyes' capability to distinguish color. That's why we use the word contrast here. If you would look at the box inside in a flash, you would judge them differently. You would think that the one on the left is lighter in color, and then the one on the right has a darker color for the box. I mean, the small box in the middle. But actually, they are of the same color. Now, what made our judgment faulty in the assessment of the image? It is the presentation of the background. So, if you would apply this concept, if you're a little bit dark skinned, so try to wear something darker so that you would appear fair in complexion. But if you are dark skinned and then you wear white, then virtually appear that you're floating on top of the lighter color. So that's how you manage it. Now this is on the color. Now when it comes to our ability to perceive differences in luminance, meaning white light and darkness, there appears to be a running dot in the middle. Now, the human eye is uh, is not an electronic device. It's made up of cells, and it functions much like a mechanical device. So, when it's dark, the iris tends to open wider. So there's the large open, like in a camera. So when it's dark, the iris opens larger because it's trying to collect light in order for you to see something. And then when it's very bright, the iris becomes small to limit the amount of light coming in. So in this case, our perception of black and white, you're trying to force your iris to be at its maximum opening and then immediately or instantaneously switching to a small opening. So the muscle becomes stressed, like it's going like that very, very fast. And in that process, we make a faulty judgment on the transition from dark, which is zero luminance, up to the maximum luminance, which let's just say 100 IRE. We call it IRE. IRE stands for Institute for Radio Engineers. One IRE is equivalent to 7.14 millivolts. So that would be the representation of bright white light as calibrated in broadcast. So imagine the difference. So if we understand the limitation of the human eye to judge color and luminance, then we can apply techniques to reduce the amount of information that we transmit, simply because we just need to entertain people. The same goes with audio. For audio, we use the psychoacoustic model, which is actually the technical representation of the human ear, the limits of what we can hear and what we don't. So, by understanding those two major concepts for the eye and for the ear, you can throw away data that can be classified as irrelevant. When we say irrelevant, it's things that you cannot see and you cannot hear. It is outside the human perception. Then why send data to represent those information? You just throw them away. Okay, that's on the part of the irrelevancy reduction. When we apply redundancy, that goes to the coding system. So in coding, especially in binary system, we have series of zeros or one. So we don't use the word redundancy anymore in coding. They call it a run length coding. So to simplify the explanation, if you have 1,000 series of ones, instead of transmitting 1,000 ones, which would represent 1 kilobyte, why not just transmit 1 byte that represents one, and then you add the parity information telling the device how many times should I repeat it. So you have substantially narrowed the amount of data to represent that example. So what are the examples of repeating patterns? So 1,000 series of zeros or 1,000 series of one, or it can be a series of 101010. So if you combine that 1,000 times, then it becomes 2,000 bytes or 2 kilobytes. So you find patterns of repetition, and then you define that as redundancy. Okay. So first, you throw away data that cannot be seen and cannot be heard. That could simply equate to about 50% reduction in data. And then when you apply coding techniques such as redundancy reduction, you can get another maybe like 30% more. So imagine. And then when you see the output, we call it perceptually lossless. It's a technical term. Um, Perceptually lossless simply means that if you compare the original against the processed version and you try to look at it like a picture, you wouldn't find the difference. The same thing with audio. I'm sure you you are aware of the MP3 standard. That's an example. It's a project by some students in Germany before, in Fraunhofer Laboratories. Um, the main objective then was to put uh, what we call portable music onto a small storage, but that was in the mid 90s. Okay, so the sensor. So if in case you didn't know, the construction or the architecture of a camera or the sensor has been patterned to how the eye is made of. Okay. Now for the display, it's actually based on the same also. The difference is that the camera sensor picks up components of light and then splits it into its component colors. A display does the reverse. So if we magnify the sensor of a camera, it is simply a combination of different um, photosensitive devices that is dedicated to red, green, and blue. We call them the RGB sensors. So if you have a smartphone, so and then the dimension of your smartphone's camera is so tiny, and then the resolution is 4K, especially for those with the new version of the iPhone and the latest Android phones. You have this very small sensor area, but it contains, if it's 4K, then you should have around 4,000, sorry, 4 million of these dots uh, embedded in it. So it's pretty cramped space already in that sensor. So the bigger the sensor is, the, the larger the gaps between the sensors, then the less detailed the image is. So the idea here is to try to squeeze them all together in that very small space, virtually leaving no gaps to provide you with the highest resolution image. But that's another technical problem for engineers because you have to apply aliasing filters because there would be less distinction already from the transition from one color to the other or luminance to that effect. When we go to a screen, so I took a photo of my television. This is a Sharp Quatron So it's based on four color system. Traditional monitors are based on the three primary colors, which I mentioned earlier: red, green, and blue. But well, as advertised by the manufacturer of this television, they added one more color, which is yellow, because in their opinion, it would provide better picture quality. So I got it, you know. So if I took a photo using a DSLR and then I magnified maximum to see what's inside. So you would see here the patterns of the different sensors is pretty much similar to that on a camera, but their actual use is in reverse. Camera captures the light while a display creates the light based on the component colors. So um, the the math that I chose for this lecture is called Discrete Cosine Transform. It's actually a two-dimensional discrete transform. So why two-dimensional? So because it's easier for us to appreciate pictures or images, and that's already a two-dimensional plane. You have the horizontal and you have the vertical. So this is the mathematical expression. But of course, your instructor, Engineer Mike Espina, is I think better qualified to discuss in detail on how this math works. So I'll go on a simpler path to explain the purpose. So it's called cosine, discrete cosine transform. And in basic trigonometry, cosine refers to adjacent. Now, when we apply the concept of adjacent, it means you are going to perform comparison between adjacent pixels. So one picture is actually, if you can split them in small parts, and then you declare each square as pixels. So it's a topic that is less difficult now for young kids. They know the resolution, so they understand pixels. Okay, now when you try to take a photo of anything, like a flower or a cloud formation, a garden, you would see similarities in the captured image. So if it's a garden, then naturally there's lots of greens. So if you have redundant colors, you can apply the algorithm of redundancy reduction there. And then we go further. By going further, we analyze the magnitude of the difference of one pixel and then the adjacent pixel. And then a decision will be made if the difference between the two is substantial enough to warrant that the second pixel be given its own um, data representation. So because if the criteria is not met, or the difference between the two falls on the category of irrelevant, meaning the human eye will not be able to determine the difference between the adjacent pixels, then the second pixel will assume the data representation of the first pixel. So you gained data rate reduction again from that concept. But this is how the math looks like, but the application is quite simple. Okay, so I have listed here two simple concepts. We need to understand the limits of what the human eye and ear can see and hear. And then number two is apply the concept of determining if it's irrelevant or if it's redundant. Until today, with the latest publication of the most advanced compression technology, H.265, you can download it from the IT website and read it. We can now achieve super high definition reception uh, by applying that compression technique. So it became possible for remote delivery of super high definition. So if super high definition can be delivered in that manner, then 4K is so easy. So we go to audio first. So MPEG-1 audio, or to be specific, MPEG-1 Layer 3 audio, also known as MP3, was developed in the 90s. Um, it allowed compression from the original CD. So when you sample one song from a compact disc and convert it into a WAV file, it's approximately around 45 megabytes in size, file size. So because it's called raw or native format. But when you apply MPEG-1 layer 3 or MP3 compression, that 45 MB file size becomes approximately 4.5. So you have achieved like 100 times reduction. And then the output is perceptually lossless. You know, the block underneath the three ones on top, the mapping, quantizer, encoder, and the frame packing. The psychoacoustic model is the mathematical representation of the human ear, and then by mapping the PCM samples, that psychoacoustic model will determine or instruct the quantizer encoder the amount of data needed to represent the PCM samples. And then the output would be called the frame packing, or how the serial bit stream would be formatted for the presentation or playback. So this is the simple concept. If this is for video, then we replace the block called psychoacoustic model with the human visual system to apply the data rate reduction. So this is where the psychoacoustic model block, that's where the engine is. That's where the math is working for you. And those calculations are performed quite fast in order for the user to not be able to feel that there's actually a delay. And we're talking of microsecond or even nanosecond delay here. That's how fast the processes are. So I jumped to MPEG-2 audio, which is the later or newer standard. It's actually called AAC, Advanced Audio Coding. So I've just listed here different applications for AAC. LC means low complexity, HE or high efficiency, AAC, HD, and so on and so forth. You see the different applications. So these are technologies that you are actually using every day without you knowing it. If you own a smartphone, a portable music player, you have a smartwatch, then chances are you paid patents to use this this codex. So if you use on your PC like Line or Facebook Messenger, I mean like the voice service, any voice service, they are using patents of this technology. So specifically, I think the one that would easily apply would be the one that has the lowest latency, means lowest delay. So that would be AACLD. So it's not low definition, but it's actually low delay. So when you call someone from your smartphone, it performs the process of quantizing, sampling, analyzing your voice, convert it into a packet or a stream, and then have it transmitted on the network. And then the other phone on the other side would have to perform the inverse process of trying to decode it. And the algorithmic delay between the process from the conversion to the transmission and to the reception, decoding on the other side, should be less than 20 milliseconds. Now, why do we need to apply such low delay? because human behavior, when you try to call someone and the other person is quite late in his response, so let's say, hello, Michael, hello, Michael. So we tend to repeat because we assume the other person did not hear what we are trying to say. That is the impact of having a large delay. So communication would be difficult or quite uncomfortable or unnatural. So that's why we need to achieve low delay. You see the different bit rates for the different audio codecs. Next, we go to video. So this is based on MPEG-2 video. So we have first on the spatial domain. So each portion of the image for the 8 by 8 pixel block, we have to convert from space to frequency. So on the horizontal, you have the increasing horizontal frequency. And then, of course, on the vertical, the direction of the arrow for the increasing vertical frequency. So the DCT, or discrete cosine transform, performs comparison in this zigzag pattern. So you have first on the top left. So that's how the algorithm analyzes the image. So it makes comparison of those pixels. Basically, they're all adjacent to one another. And then after performing this on an 8 by 8 pixel block, they will arrive at a number to represent that 8 by 8 pixel block. So it still doesn't make sense, right? So this one is a good example. So this is a picture, but if we are to represent it as a form of pixel, okay, of course, that's an exaggerated representation of the pixel. And I took a sample of a person somewhere in the eye of this lady. So you will see that it's actually composed of various squares or pixels. And then from this representation, you would see that there are actually a lot of redundant pixel blocks. And then there are adjacent pixel blocks that have very little difference to one another. So by knowing those two, we can now apply the concept of irrelevancy and redundancy. Okay, so this is a picture. So in a picture, we use what we call intra frame scanning. When we say intra frame, it means we scan the the similarities and the difference of an image within that one particular frame. That's why intra frame, within this one frame. If it's video, we use intra-frame and interframe, which means interframe means comparing the difference between the two frames, two pictures. So anyway, the video is represented by a series of pictures actually that mimics motion. It looks like it's actually moving, but it's actually the speed of the presentation of the number of pictures or frames in front of you that creates the illusion of movement. And when you shoot a video, you are virtually capturing almost the same redundant images at your background. Like when you're watching me now, if it's an MPEG coder, it would only, the coder would concentrate on the things that are changing periodically. So if it's me talking, you're watching on the video now, my background remains the same all the time. So the MPEG coder actually is transmitting what is moving. So if it's me doing this, then the coder would have to perform the coding and transmission of me moving like this. This is also the reason why reporters on the field try to be stationary. And then they go like this with the microphone. And virtually it's like the only thing that is moving is their mouth. It's like, ladies and gentlemen, we are here in Florida to report about the tornado. So when they try to limit the movement to their lips, it means that there might be some bandwidth constraint in their transmission. So by limiting the movement, you are using very small amount of data to allow the transmission and reception of an encoded video stream. We'll go to that. Okay. So from that, this enhanced portion, the magnified portion of the eye of this lady, if we put values on it, okay, so from the original picture for the DCT here, 8 by 8 pixel, you see the vertical, it looks like the first two columns looks like they're all white, and then the second two, and so on and so forth. But if we actually put the values, the mathematical sampled values for each column, you would see here that the first column is valued at 223 from top to bottom, okay, from the increasing frequency. And then if we go to the extreme, which is represented as purely black column, the darkest one is represented by 16 on the highest horizontal frequency going down to the highest vertical frequency. So that's where the similarity lies. And then when we apply the DCT algorithm, the DCT coefficient shows from the 8 by 8, it shows you very minimal data to represent the image. And the rest are represented as zeros based on the coding. So if you have to repeat it, you have an 8 by 8 pixel, and then the resolution of the picture you're trying to process, let's say, is like in 4K. So your coder will have to process that almost instantaneously. So it's like when you open a picture, and if it loads like 5 seconds, people get impatient, but they don't understand the amount of computing power behind trying to show the image immediately so that you'll be happy. Well, most of the time now, when we click a particular image, it just flashes on the screen immediately. So that's the advantage and the convenience of technology now, thanks to the math behind all of these technologies developed by engineers. Okay, so how does the increasing horizontal frequency looks like and the vertical also? So if we look at, you look at on the frequency domain here, the blocks. So the first combination of the lowest horizontal and vertical frequency is simply a square, a white square. And then if we move to the right, the next stage, the white square is divided into two vertically. So it becomes like two rows. And then as you increase the frequency further, you see the pattern, how it develops. So it's actually increasing horizontal frequency, but the pattern is in vertical. So if we look at the vertical side, okay, the pattern is horizontal. So until you reach at the bottom right of both, you will see what we call the checkered pattern. So any part of the image would be a sort of any of the patterns that is shown here. So it becomes like a template. It is used to represent a particular portion of the image. So when you go to the bottom of the highest vertical and the highest horizontal frequency with the checkered pattern here, that is what we call the worst case condition. It means that at that level, there can be no compression that can be done because there is simply no relationship between the adjacent pixels. In a checkered pattern, if you have a white pixel, the adjacent pixel would be black. So there is no difference. Definitely, you cannot apply irrelevancy because they're at the extreme. Maybe you can perform redundancy, maybe, but that is what we call the mathematically uh, worst case condition. Now, the good thing is that it only exists in the mathematical domain. In the real world, You will not see a person walking around like a checkered pattern. Imagine you have white, black, white, black, white, black, white, black. So that is not natural. So in any naturally occurring image, the worst case condition simply doesn't apply at all. So that's a good thing. So what dictates the cost of a particular device? I'm sure you've asked this many times. You go to an appliance center, you look for a television, and you look for the best television system. You would find that those with established brands tend to be more expensive than those less known brands, but they are of the same resolution. Now, the key here is the ability of the chipset that they are using and its ability to perform decompression or for a camera compression at the highest level, which means the higher the complexity of the coder and decoder going almost near the worst case condition on this example. So if you buy some units that is cheaper, then most likely the ability of the chipset and the coder in it would be less that near of the worst case condition. So it has lesser performance. That's the difference. But if it's me who's buying television, I have all the tools. I even have a small magnifying glass that allows me to immediately look at the pixel layout of each monitor. So I know which one has the highest quality, even on the phones. So I do that, but we're engineers, that's what we do. Uh, we eat math breakfast. Okay, now we go for motion prediction. This is the one that performs interframe compression. So this image, as an example, this guy is about to kick the ball. But let's assume for a time that the guy didn't move and the ball is affected by gravity. So if the guy remains stationary like this, the MPEG coder will see and code the ball because it is the one that is moving. So at the I frame, the ball is positioned at the knee, and then at the B frame, it's somewhere in the middle of both legs. So the coder would predict that in the pattern of the direction, the coder will simply push the pixels of the ball to the next assumed position. That's what we call the motion prediction. So the I frame is the real frame, B frame is the bidirectional frame, and P is the predicted frame. Now, motion prediction is done by the MPEG coder based on the DCT analysis of frame 1 and frame 2 and frame 3, and then performing comparison, we call the delta, and then just transmit the difference among frames. So it can be a series of frames in order to achieve a significant data rate reduction. The application of the motion vector is widely utilized by the coders. Meaning a motion vector, that's why we put a square on the ball. Those are, all of them are composed of pixels. So the arrow simply tells them to move to this direction. It simply pushes the same pixels without coding them further. Push, because that is what we assume that the next position is. So the moving picture, so we have here a series of frames. So imagine there's a fly in the video. So at a certain amount of time, the fly would be at one position, and then time is equals to 0 plus 1 to the next position, 0 plus 2, and so on and so forth. So that's the only information you transmit in a moving picture or a video, be it as MPEG-2 video for your DVD, MPEG-4, or H.265. So the difference in the group of pictures, that's what we call it, GOP, group of pictures. Okay, next is the experimental results stemming from eye tracking, which means the amount of human attention to components of a picture. So at the source level here, that is the original picture, you see the density map. And then when you go to the right, that is what the human eye is actually seeing. So the saying that you look but you didn't see actually applies to us every day. This is how less sensitive we are to the existence of other components of the picture that we see every day. It can cause accidents, because you are not focused enough to look at the road. And some people actually are eating while driving. By law, it's not allowed actually. So this shows us that the human eye really needs to step up, because the sensors now that are being developed are already at the same level of what the human eye can see. And for the motion vector, so captured from a software for testing images, you will see that in this image, the object on the head of the baby has a lot of those lines. Those are the motion vectors. Okay, so and then the rest are not moving, stationary. So the coder would not transmit or not repeat the transmission of those bits because they are of the same position, magnitude, dominance, and prominence. And then look at this one is from the matrix. So when the agent captured Morpheus, so on the top you see the agent walking. So it represents about maybe less than 25% of the actual image has motion. So the direction of those lines shows the next assumed position of the pixels based on the coder's judgment. And then when we look at the picture of the agent, this is even like less than 20%. So you see, it's only the hand motion. So it's predicting where would be the next position of those pixels. And then the part where Morpheus is displayed here. So instead of the motion vector, they place a color coding of the pixel components. So to make a better judgment of what looks like the same or not. Okay, next we go to super high vision or super high definition format. I don't know if you are aware of this technology, but it's been developed since early 2000. Because when I did my engineering research in NHK Laboratories in Tokyo, they are already building the prototypes and they have a theater, an experimental theater to showcase super high definition. Now, to give you an idea, super high vision or super high definition is 16 times of high definition, 16 times the quality. So when you watch super high definition, you get immersed, you you become part of the video, the thing that you're watching. You lose track of reality and what you see is actually becoming reality. That's how beautiful super high definition is. Now, digital cinema is equivalent to almost 4K. So if you knew 4K, and I assume most people listening now have 4K TVs in your homes, you would need around four at least, take 4 to 8 of 8K to mimic super high vision. That's how amazing the resolution. And super high vision covers 99.9% of what the human eye can see. So first, when in the analog days, this is the resolution of most television sets. And then when digital television came in, and then there's high definition, this is the resolution of your 1080i television set. And then 4K came about, and it's nice. It's enough to impress people for 4K until you see super high definition. Now, all of these things that I discussed stemmed from the basic concepts of discrete cosine transform and the fast Fourier transform. To minimize the required time to perform the calculation, the Fourier transform simplifies the image representation of a particular combination of waves from 1 to 1000 to 8000, whatever. Discrete cosine transform allows us to mathematically represent each pixel component based on the concept of irrelevancy and redundancy. This is how the theater is envisioned. You have 22.2 audio and you have the screen. You get immersed. So if it's a drama, somebody dies, for sure you're gonna cry. When I watched a sample video here, there was a big steam locomotive that is running towards me. I immediately jumped because I thought the train would hit me. That's how real it is, the experience. So this is the one that shows the color gamut, the representation. So the curve line, the thin curve line outside represents the limits of what the human eye can see. So anything outside of that virtually is invisible to us. So high definition is the blue line, and then the red line shows you super high vision or super high definition. And that accounts for 99.9% of what we can see. So somebody would develop maybe a 16K video resolution in the future. Sure, the technology would allow us to do anything we want. But is it practical? Is it something usable? The answer is no, because we've already reached the limit of what we can perceive. That's the limit. We've reached that already. So I've reached the end of my presentation. I'd like to share some photos of my international awards for my work in digital television. So even before the K-pop industry became a major hit worldwide, I was there standing in the KBS studio and a live high definition broadcast. It's quite unfortunate. There's only about 20 Filipinos in the crowd, and most of them are representatives of the KBP. So yeah, and I have a book called ISDB-T Handbook for Broadcast Engineers. You can buy it in Amazon, and I don't earn anything from this. It's more of like helping people interested in digital broadcasting to learn more and make it easier for you to perform your job. So thank you for listening. I'll turn over to Michael and wait if there's any question. Thank you, guys.
Okay. Thank you very much, James, for sharing your knowledge and expertise in ISDTB. Probably I'm gonna buy few few probably pieces of this book, and I would share it to my followers, maybe a raffle or something, or drawing if they gonna win something, and then I'll share that book to them.
I wish I could
Um
sign it.
yeah. Probably when I go home to the Philippines. Okay, there are actually a couple of questions here, James. So since our audience is from high school to college and maybe some are professional working, so the questions are really diverse. Some are basic, some are probably advanced. So let me read to you the first question. So I think you mentioned this earlier in one of the slides you shown us. Why do we need to throw video or audio in the coding techniques you mentioned? So is there like a purpose or a goal for that?
Well, in the field of communication, the major limiting factor in any link from the origin to the destination is the bandwidth. We have limited bandwidth. Now,
Okay.
of course, when these technologies were developed, we're talking of kilobytes of bandwidth, but now we're talking of megabytes or terabits in transmission. So those are the limitations. So you cannot achieve the transmission. So you have to find solutions to enable the link to work. So by developing data rate reduction techniques, you are able to achieve large network connections. So it's just that many people take for granted the benefits of what they enjoy now, but those are the fruits of the labor of the people who work hard in the old days uh, to achieve efficient delivery of audio and video. So, um, typical example for a video, if you try to watch, I don't know if you remember the 3GPP when Nokia was the thing for phones. When
Yes. Mm-hmm.
you shoot a video using a Nokia phone, it is compressed based on 3GPP. That's the format. And you
Mm-hmm.
see immediately the pixels on the screen because that's the limitation. So it's not really defined. So it was enhanced further by making better sensors and better algorithm. So the picture detail becomes improved without increasing the amount of data to represent the same image. So now you can even like Netflix. Netflix is using like an MPEG 4 H.264. I believe in the future they'll be using H.265 that will even cut the video data rate into half. To give you an
Wow. Okay.
example, high definition uncompressed is actually 1.5 gigabit per second. Per second.
Wow.
But
Mm-hmm.
when you apply H.264 or MPEG 4, it's reduced to around 6 megabits per second only. From
Mm-hmm.
1.5 gigabit to about 5 to 6 megabit per second. So imagine how much data we've thrown away. It's like
Mm-hmm.
more than 90%, and you still don't see the difference between the original and the compressed version. So I guess that answers it.
Okay. So basically the bandwidth limitation, right? Okay. So next question, James, is I don't know if you already mentioned this in the presentation, but the question is, what are the advantages of high definition digital TV broadcasting compared to analog?
Okay.
Mhm.
Number one is noise immunity. In the analog days, I don't know if you've seen analog broadcasts at all. So there is a degradation of the picture quality in direct proportion with the amount of signal level you're receiving, which means if you're too far away from the transmitting station, then you get an inferior signal from the people who's closer to the transmitter. So that's one factor. Number two is the presence of noise in the environment, like a white noise, impulse noise. Sorry, it distorts the image. In digital, that doesn't exist. So the person near the transmitter and the one that is farthest and still within the signal level can see the same video quality, clear, noiseless. The only disadvantage of digital television is that when you reach the portion of the area that you're too far away to have substantial reception, there is no degradation. You simply don't get the signal. It's like 1 and 0. It's either 0 or 1. Either you get it or you don't.
Okay. Thank you, James. And then we still have like few more questions here. What are the transmission principles behind digital TV? This is, I think, more technical. Probably an engineer would ask this question.
For the transmission, the most successful model is using the multiple carrier system, the OFDM. The Europeans uses the COFDM or coded orthogonal frequency division multiplexing. The Japanese system uses BST OFDM or band segmented transmission orthogonal frequency division multiplexing. The North American standard called ATSC has undergone significant revisions of their initial standard that allows them to do mobile television already. That was the
Okay.
major limitation of the ATSC system before. Uh, which is why there's only a few countries using the North American standard, and that's the US, Canada, Mexico, Taiwan use us. Is it? I think Korea, South Korea. So those are the four countries using ATSC. Imagine we have so many countries around the world, and there's only four using the American standard.
Okay. All right. Thank you, James. And then I think this is a question from a high school student. So what course in college do I need to take to be able to do research in digital TV? Or probably he wants to be a, a broadcaster, an engineer or broadcast engineer like
If,
you, James.
if you're outside of the Philippines, especially if you're in the US or North America, then the course you should take is electrical engineering, and then you should take the track for communications. Um, so be prepared. There's a lot of signal analysis that you need to learn. Those are the principles. Once you master the principle, it's easy when you do the application.
Mhm.
Uh, that's the tip. But if you're in the Philippines, we have a separate course in the university called Electronics and Communications Engineering. It's a derivative, specifically. I mean, it's a derivative from the electrical engineering, but it focuses specifically on electronics and communications. So that's my advice.
Okay, thanks, James. And then I think these two questions are related, so I'll read them both. What is the next trend in digital TV? And then would hologram be part of the home appliances in the future? So those two questions.
Okay.
More futuristic questions.
Yeah, actually, it's closer to reality than fiction. So there was, I saw a demonstration that was meant to be used for the Tokyo Olympics. It uses two 8K video, two high definition streams, and then they would be able to project the virtual image in front of you in 3 dimension without the use of a glass. So uh, I'm gonna look for it. The demonstration of NTT Docomo. It's they call it. I forgot the Japanese word, but there's already a YouTube video on this one. So
Mm-hmm.
like there's a sporting event, an indoor sporting event, like a judo. Of course, that event area can only cater to a limited number of people. So, but if you want a lot of people to watch the same event, you can actually project the same event into a stadium. And
Oh,
if you can
wow.
do that to a stadium, you can transmit it to other countries, fill it up with people, and you would see giants in front of you
Mm-hmm.
doing the sumo. So I'll try to remember the keyword in Japanese. So
Okay. Probably you can share it to me, James, and then I'll share
yes,
it to the
yes.
to our followers. Okay. Thank you, James. And then the last question. So this is not a math question, but the person might be curious. What are the mathematics behind used in the 8 by 8 pixels? Does it uses or apply the matrix algebra in doing the 8 by 8 DCT or TDCT? I think
Hmm.
you've shown that
But
earlier.
to represent the mathematical equivalent of each pixel in an 8 by 8 block, you perform the DCT scanning. So the
Mm-hmm.
discrete cosine transform, zigzag scanning. And then once you have established the values to represent that 8 by 8 pixel block, then that's the time you apply basic arithmetic or some algebra to
Mm-hmm.
further reduce the data rate. So it's not only DCT, but it's a combination of various mathematical proofs that that would simplify the representation of a group of pixels into like a single number only. Much
Okay.
like the Fourier transform that I mentioned, it is dealing with thousands of carriers, but at the output, it's represented by a single wave.
Yes. Mhm. Okay. Thank you, James. And I think that's the last question from our viewers. Okay. James, do you want to promote where can they contact you or they can see you from you have I know you have a YouTube account or maybe a Facebook page that you
Yeah.
wanted to promote. Yes.
My Facebook page is my personal page, but you can message me there. It's James Rodney Santiago. And on YouTube, I have uploaded some lessons in engineering and some crazy stuff that I do, just to promote my page. It's also James Rodney Santiago. So I don't use virtual names. It's just me. So yeah, that's the only two accounts that I maintain.
Okay, so you can find him easily in YouTube and in Facebook, right? With your name. All right. Thank you, James, for sharing your expertise. Hope we can invite you again next time if you're not busy. Okay, I know you are busy, but thank you. It's a pleasure and honor to have you here in Math Agility Live. So, and also to our followers, thank you for watching us today. And if you have any questions, you can write down at the comment section below of our Facebook page. And you can also, of course, subscribe to Engineer James' YouTube account and Facebook page if you have any other or further questions about broadcast engineering and the mathematics behind it. So, again, see you next Thursday. God bless everyone and stay safe. Bye, James.
Thank you. Bye bye.
Thank you.